Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 14. In this lecture, we'll discuss the Doppler effect. This topic is covered in Chapter 17 of our textbook by Surway and Jewett. To better understand two-dimensional and three-dimensional waves like sound waves, we need to introduce the notion of wavefronts. Consider a wave at one instant in time. At that particular moment in time, mark all the points that correspond to crests. Remember that crests for sound waves, for example, correspond to points where the displacement is maximum. These points together define the wave fronts of the wave. You've probably seen wavefronts before if you've seen ripples on water. So imagine a calm pool of water, and then imagine dropping a couple of pebbles into that pool, or maybe tapping your finger in the middle of that pool of water. You generate water waves. These water waves spread out in circles and propagate outward. The ripples that you see are essentially wave fronts of the wave. Wavefronts are just another way to represent waves. They're especially useful for two-dimensional and three-dimensional waves. Here I'm defining wavefronts as basically all the crests of the wave, but it really could be any other point along the wave. So you could mark all the troughs of the wave, and you would still get wavefronts. In fact, any set of points having the same phase could be used to define wavefronts. Wavefronts provide a nice visual representation of waves for us. When you look at a picture like the one shown here, you need to recognize that each circle corresponds to a specific phase of the wave. More specifically, you can imagine that each circle corresponds to the peaks of the wave, or each circle could correspond to the valleys of the wave. The important thing is that all of the points on a given circle must be doing exactly the same thing. When you see a picture with two different colors like the one shown here, then you could imagine that one set of circles, like the green ones, represent peaks, while the other set of circles, like the red ones, represent valleys. It's helpful to imagine that you're looking at water waves in this type of a situation. It's helpful to imagine that you're looking down on a pool of water and you're generating water waves by, let's say, tapping your finger in the middle of this pool of water. As you do so, you create ripples that move outwards. These circles are essentially representing those ripples. If you were to take a cross-section of this body of water, if you were to look into the body of water, so to speak, you would get to see the sinusoidal representation of waves that we've been using for the past few lectures. The red circles here correspond to the peaks of those sine functions, and the green circles correspond to the valleys of those sine functions. Given the sinusoidal representation of a wave, you can look at the distance between two peaks and measure the wavelength. Similarly, given the wavefront representation, you can look at the distance between two circles and measure the wavelength. So these two wavelengths are essentially the same number. However, they are measured slightly differently for the two different representations of waves. Now that we understand the wavefront representation of waves, we can finally talk about the main topic of this lecture, namely the Doppler effect. The Doppler effect refers to the fact that the perceived frequency of sound waves at a detector may be different from the generated frequency at a source due to motion. Notice we're talking about two different frequencies here. We're talking about the original frequency generated by a source, like an audio speaker, and then we're talking about the perceived frequency that is detected or heard by a person, for example. Naively, you might think that these two frequencies should be the same, but in general, they are not if there is motion involved. In this picture here, for example, we have a noisy motorcycle. The motorcycle is the source of the waves. And then we have two detectors, essentially two people that can hear these sounds. The detector on the left is at rest. This person is not moving, but the detector on the right is moving. The motion of the source and the detector could result in a change in the perceived frequency. So in general, the source of the sound, for example, a loudspeaker or a noisy motorcycle, may move. The detector of the sound, for example, the person or perhaps a recording device, could move. And also generally the medium of sound could move as well. For example, it is air that is carrying these sound waves. The air itself could move if there is a wind blowing through this region. In our class, we will not consider this third type of motion. We will always assume that the medium is at rest, but we will discuss how the frequency changes when the source and the detector are moving. To make our discussion of the Doppler effect more precise, we need the Doppler formula. If a moving source emits sound with a frequency f sub s, then a moving detector receives sound with frequency f sub d, where f sub d and f sub s are related by the Doppler formula. According to this formula, the detected frequency and the source frequency are not necessarily equal to each other. In this context, the source could refer to a person simply talking, but it could also refer to a noisy motorcycle, an audio speaker, or a musical instrument being played. The detector could simply refer to a person listening, but it could also refer to a recording device. C is the normal speed of sound. C represents the speed of sound when nothing else is moving. So the measured speed of sound when the source, detector, and medium are all at rest is considered the normal speed of sound and represented by the letter C in this equation. V sub d is the speed of the detector, and V sub s is the speed of the source. According to this formula, if the detector and the source are at rest, then V sub d is 0 and V sub s is 0, and of course C over C is 1, in which case the detector frequency and the source frequency are going to be equal to each other. That would be the case, for example, if you're sitting in a concert hall listening to a musician play a violin. The frequency that the musician generates on his violin is going to be the same frequency that you hear while seated in the concert hall. On the other hand, if the violinist is moving, for example, if he's running away from you, then the frequency that you hear is not necessarily the same as the frequency that he's playing. Or if you're running towards the violinist, then again, the frequency that you hear, the detector frequency, is not necessarily the same as the frequency that he's playing, the source frequency. To use this formula correctly, you need to understand some conventions regarding the signs of V sub d and V sub s. Normally, when we talk about speed, we have the magnitude of the velocity vector in mind, so we think of speed as a positive quantity. In this particular equation, either one of these v's could be positive or negative. The source speed is positive if it is moving towards the detector, but it is negative if it is moving away. Similarly, the detector speed is positive if it is moving towards the source, and it is negative if it is moving away from the source. So keep in mind that there is already a minus sign built into the equation, but in addition to this minus sign, V sub s could be positive or negative itself, depending on whether it is moving away or towards the detector. This convention is essentially based on the distance between the detector and the source. If the distance is decreasing, we say that they are moving towards each other, in which case the speeds are positive. On the other hand, if the distance is increasing, we say they are moving away from each other, in which case the speeds are negative. Knowing when V sub d and V sub s are positive and when they are negative is essential to using this equation correctly. Lastly, I should mention that our textbook by Servoy and Jouet uses a slightly different notation for this particular formula. Instead of f sub s and f sub d, they use f and f prime, and instead of c for the speed of sound, they use v. You're free to use whichever equation you want, however, I will continue to use the equation shown here for the rest of our lectures. I have a lot more to tell you about the Doppler effect. However, before moving on, let's make sure you're comfortable with the use of the Doppler formula by doing a practice problem. In this problem, a driver travels northbound on a highway at a speed of 25 meters per second. A police car traveling southbound at a speed of 40 meters per second approaches with its siren producing a sound at a frequency of 2,500 hertz. So the police officers sitting in the police car hear this frequency. 2,500 hertz is the source frequency. In this context, the police siren is the source of the sound. The driver in the other car, however, will not hear a frequency of 2,500 hertz. The frequency that he or she hears is going to be determined by the Doppler formula. Specifically, we want to consider two different scenarios. In scenario A, we want to know the frequency that the driver hears as the police car approaches. And for part B, we're asked what is the frequency that the driver hears after the police car passes him. We can represent these two scenarios like so. On top, we have the driver and the police car approaching each other. And on the bottom, the driver and the police car have passed each other, so they are receding from each other. In the first scenario, the distance between the two is decreasing. In the second scenario, the distance between the two is increasing. We have all the numbers that are necessary for the Doppler formula, so we can just plug those into the Doppler formula and find the answer. In scenario A, the source frequency is 2,500 hertz. We do need to know the normal speed of sound. In most cases, we will assume that the normal speed of sound in air is 343 meters. We need to know what V sub D is, and in scenario A, the speed of the driver, the detector in this case, is 25 meters per second, so that goes in here. And the speed of the source is 40. The speed of the source in this context is positive 40, and the Doppler formula has a minus sign cooked into it. We can now plug all this into our calculator, and we find that the driver, in this case the detector, would hear a higher frequency as he approaches the police car. He hears a frequency of 3,036 hertz, while the police officers hear a frequency of 2,500 hertz. We plug the numbers into the Doppler formula for the second scenario and get a slightly different answer. In the second scenario, notice that V sub D, speed of the detector, is now minus 25. That's because the detector, or the driver in this context, is moving away from the police officer now. Similarly, the police is moving away. The distance between them is increasing. We can say the police is receding from the driver. So the speed of the police is now minus 40. Plugging these numbers into Doppler formula, we find that once the police has passed the driver now hears a lower frequency, a frequency of 2,076 hertz. So we now want to develop a conceptual understanding of the Doppler effect. We want to understand conceptually, or more intuitively, exactly why the detector frequency is not equal to the source frequency. To understand this phenomenon, consider this simple animation. In this animation, I have a source at the center of the screen, and this source is capable of generating sound waves. The source could be an audio speaker, but imagine the audio speaker is inside a car, for example, because we want the source to be able to move. On the left and on the right, I have two detectors. So these could be basically two individuals standing by the side of the road, listening to this music or to these sound waves. To begin with, we're going to assume that the source speed is 0. So the speaker is not moving, but it is generating sound waves. I'm representing the sound waves using wave fronts. So each one of these circles represents, let's say, the peaks of the sound wave as the sound waves propagate outwards. When these peaks reach the detectors on the left and the right, those two detectors can hear or detect the sound waves. Now, this animation isn't very interesting because the source is at rest. So let's give the source a little bit of speed. Here, the source speed is 0.2c. So the source is moving at 20% the speed of sound. And of course, as it is moving, it is generating sound waves. You can see the wavefronts. Each one is a circle that moves outwards. The speed with which each circle propagates is simply the speed of sound, which we're calling c. Let's now speed up the source a little bit. Now the source is moving at 0.4 c. Notice once again we have circles that are propagating outwards, but the circles are no longer concentric. The circles have different centers. The center of each circle is basically the instantaneous location of the source when that particular wavefront was generated. And now you should notice something interesting. Although we have a set of circles, the circles appear to be bunched up on the right and separated on the left. This fact becomes even more prominent when we speed up the source. Now the source is traveling at 60% the speed of sound, and you can clearly see that the wavefronts are bunching up on the right side as we approach this detector, but on the left side, as we recede or move away from this other detector, the wavefronts are separated from one another. This is an important fact because remember, the wavelength of sound can be measured by looking at the distance between two wavefronts. Now the source is moving relatively fast. Now the source is moving at 80% the speed of sound, and you can really see this phenomenon. You can see that on the right side, the wavelengths are extremely short. If you ask the detector on the right, the person standing on the right, to measure the wavelengths, he would measure a very small number. On the other hand, if you ask the person on the left to measure the wavelength, he would measure a large number. So basically, the wavelengths that are measured on the left and on the right are going to be different. And of course, wavelength is related to frequency. If you change the wavelength of waves, then you're going to change the frequency of the waves. So ultimately, the frequency that is heard or detected on the left is going to be different than the frequency that is heard or detected on the right. So let's summarize the discussion on the previous slide. We want to know what happens when the source is moving. When the source moves, the wavelength changes. Whether it increases or decreases depends on whether the source is approaching or receding from the detector. In either case, the wavelength changes, but the wave speed remains constant. So the speed with which each individual circle travels outwards remains constant, but what that means is that the frequency must change. After all, remember that the wavelength, wave speed, and the frequency are related to each other. They are related by this equation here. You may have seen other versions of this equation in the past. We have mentioned that for all waves, not just sound waves, V is equal to lambda over T, where T is the period. Recall that frequency is simply 1 over the period, so these two equations are really the same. However, in the context of the Doppler effect, it's more convenient to speak about frequency and wavelength. So according to this equation, if V remains constant, and I've represented that fact by putting a circle underneath the V, and lambda changes, then F must change. If lambda happens to go down, then F must increase. But of course, if lambda increases, then F must decrease. So this is the essence of the Doppler effect. Motion of the source causes the measured wavelength to change, and that forces the frequency to change. Of course, we've really only discussed half of the Doppler effect. We've been talking about what happens when the source moves, but what happens when the detector moves? So here you can imagine the source is at rest and one of the detectors is moving towards the source. In that case, what changes is the wave speed. So as the detector begins to rush towards these wavefronts, the speed that he measures for these wavefronts changes. The wavelength, on the other hand, remains constant. You can see the separation between the wavefronts on the left is the same as the separation on the right. However, if the wave speed changes and the wavelength doesn't, then the frequency must change. Once again, V must equal to lambda F, but in this case, lambda remains constant. V changes, it might increase, in which case F would also increase. The Doppler effect has many applications, in part because it can be applied to all waves, not just sound waves. We've been talking about the Doppler effect in the context of sound waves because sound waves can be heard and they can be more easily or intuitively understood, but in general, the Doppler effect and the Doppler formula can be applied to all kinds of waves, including electromagnetic waves, which we will study in later lectures. If you've been unfortunate enough to receive a speeding ticket, then you might be familiar with one application of the Doppler effect in police radar guns. The radar gun sends out radio waves, which then echo or reflect from a car. As far as the reflection is concerned, the car is the source of that particular wave. The reflection returns back to the radar gun and its frequency is measured by the radar gun. The change in that frequency basically can be used to figure out how fast the source, that is the car, was moving using the Doppler formula. If the car is not moving, if it is at rest, then the frequency will not change at all. But if the frequency changes by a lot, then that means that the car must be moving very fast. The Doppler effect is also used in the Doppler weather radar. If you've seen images like this of cloud movement over land, it's been generated using the Doppler effect. Essentially, a large radar sends out signals, radio waves, to clouds. Some of these radio signals echo back, they reflect back to the radar. And again, by measuring the change in the frequency of the reflection, a person can measure the speed with which clouds must be moving over land. The Doppler effect is also used in medicine. The Doppler echocardiogram can be used to measure the speed of, for example, blood inside the heart. So what you see in this animation here is blood actually rushing in and out of the heart as the heart pumps. Again, here we can measure the speed of the blood by simply looking at the change in the frequency of the echo or the reflected waves. So let's end this lecture with a practice problem. A police car, let's call it car B, carries a siren with a frequency of 2,500 Hertz. Consider the two scenarios shown below. Calculate the frequency heard by the race car, we'll call that car A, in each of the two scenarios. On the left, car A is moving with a speed of 25 meters per second towards car B, while car B is at rest. So we can say the detector is moving, but the source is not moving. In the second scenario on the right, car B is moving towards car A with a speed of 25 meters per second, while car A is at rest. So we can say that the detector is at rest while the source is moving. And the question is, in each of these scenarios, what is the frequency that car A hears? So the police officers in the police car would hear a frequency of 2,500 Hertz, but what does car A hear? We can use the Doppler formula to answer this question. The source frequency is 2,500. The speed of sound, the normal speed of sound, is 343 meters per second. The speed of the detector is 25. Notice it's plus 25. So what's in the parentheses is a positive number because car A is moving towards car B. And of course, the speed of the source is 0 because the source is not moving. Plug these numbers into your calculator and you will see that the driver of car A will hear a slightly higher frequency, a frequency of 2,682.216 Hertz. Now you might think that the answer for this second scenario should be exactly the same as the answer to the first scenario. However, if you plug in the numbers, you'll see that the answers are slightly different. On the right, velocity of the detector, that's car A, is 0, and velocity of the source is plus 25. Note that the formula has a minus sign, and then what's inside the parentheses is plus 25 because car B is moving towards car A. If you plug these numbers in, you'll see that the person in car A hears a frequency of 2696.541 Hertz. So there is a minor difference between these two scenarios. That difference arises from the fact that when the source is moving, the wavelengths of the waves changes, but when the detector is moving, the wave speed changes. That subtle difference between the two scenarios means that you have to be very careful when you apply the Doppler formula to the two scenarios shown here. And that is the end of this lecture. Thank you for your attention.